Let's work on the following problems. Let's evaluate square root of -11 squared. So the way it's written, this becomes square root of positive 121, which in its own right becomes positive 11. In the next problem we have square root of 144 plus 25, so we need to do the addition first. 144 plus 25 is 169. Square root of 169 is 13. Then in part C we have square root of 144 plus square root of 125. Here we can do each square root individually. We get 12 for the first and 5 for the second, so we add them up and get 17. Then cube root of -125. Since this is an odd degree root, we can factor out negative, and we get cube root of 125 with a negative sign up front. And then cube root of 125 is 5, so the complete answer is -5. Then the fourth root of 1 over 81. So it's, fourth root of 1 is 1, and we are left with fourth root of 81 in denominator, and that works out to be 1/3, since fourth root of 81 is 3. Then fourth root of -2, all of that squared. We need to do -2. Let me say it again. This is fourth root of -2 to the fourth power, so we need to do -2 to the fourth power first, which is 16, and then we do fourth root of that, and that's +2. Then fifth root of -4 to the fifth power. Again, we need to do fifth power of -4. That will be -1024. And we do fifth root of that. So as before, this is an odd degree root, so we can pretty much take negative outside. This is -fifth root of 1024, and that works out to be -4. And the last question, true-false question: does the following identity hold for all a and b? So is it the case that square root of a plus b is equal to square root of a plus square root of b? Well, what we need to look at is these two problems. So we have square root of 144 plus 25. Square root of 144 plus 25 is 13, but square root of 144 plus square root of 25 is 17. So those two things are not equal. So this identity does not always hold. So the answer is false. And more often we get that square root of the sum of two numbers is different from the square root of one number plus another number. Now in problem 2 we're going to work on simplifying expressions involving radicals. In the first problem we have a fraction with square root in numerator and denominator. So by the rules for the roots, we can turn that into a single square root of the entire fraction. And then we can work on numbers separately. So there is an 8 hiding inside of 72. So if you cancel 8 and 72, there is 9 left. So that's what we're going to be looking at. And then there is 1x downstairs, and one of the 3 x's upstairs will be cancelled. So we're looking on square root of 9x squared over 1, technically, but we don't put 1 downstairs. And then square root of 9 is 3, and square root of x squared is x, as long as x is a positive number. So if you have square root of a product of terms, you can do things, you can do square root term by term. In the next problem we have square root of 6x cubed times 3x. So we cannot do square root of 6 right away, and we cannot do square root of x cubed right away. But what we can do, we can split x cubed into x squared times x. And then we would be able to do square root of x squared. So we can do, so I'm gonna move 3x up front. That's where that 3x comes from. and then square root of x squared, that thing becomes x. And then square root of 6x stays the same. So then we multiply x by that x, and we get 3x squared times square root of 6x. Then in problem C, we have square root of 63x minus square root of 28x. So we'd like to split out a perfect square, if possible. 63 is 9 times 7, and 28 is 4 times 7. So we can do square root of 9, this is 3, so square root of 9 becomes this 3. Square root of 4 becomes that 2. And we're looking on 3 times square root of 7x minus 2 times square root of 7x, so that's that's 1 times square root of 7x, but we're not writing 1 up front. Similarly, in part D, we have 4 times square root of 12 minus 2 times square root of 75. 12 is 4 times 3, and 75 is 25 times 3. So we can do square root of 4 and square root of 5. And things are still multiplied, so the square root of 4 becomes 2, square root of 25 becomes 5, and we're looking on 8 square root of 3 minus 10 square root of 3, so that will give us negative 2 square root of 3. Then in part E, we have 4 different radicals added or subtracted together. So we'll try to figure out any perfect squares out of this. So it's 3, then 54 is 9 times 6. 24 is 4 times 6, 96 is 16 times 6, and 63 is 9 times 7. So we can do a bunch of square roots. So the square root of 9 is this 3. Square root of 4 is that 2. Square root of 16 is this 4, and square root of 9 is that 3. And things are multiplied, so we have 3 times 3 minus 2 times 2 minus 4, and then plus 4 times 3. So we do the math, and we have 9 root 6 minus 4 root 6 minus another 4 root 6 plus 12 root 7. Only the first 3 terms have the like radicals, square root of 6, so we combine those 3 into a single square root of 6 plus 12 square root of 7. Then in part F, we have cube roots. So we'd like to split 24 into some perfect cube times something else. And conveniently, 24 is 8 times 3. Likewise, 81 is 27 times 3. So cube root of 8 is positive 2. Cube root of 27 is 3. So we're looking essentially on 6 times cube root of 3 plus 3 times cube root of 3, and that definitely works out to be 9 cube root of 3.